In this video, we're looking at double angle identities. So we have our double angle identities listed here. Cosine of 2a is equal to cosine squared a minus sine squared a. Now, be careful, this is similar to our Pythagorean identity, but our Pythagorean identity has cosine squared a plus sine squared a, so that sign difference. We want to be mindful of that. And then we have two other formulas for cosine 2a. The second is 2 cosine squared a minus 1 and 1 minus 2 sine squared a. One double angle formula for sine of 2a is 2 sine a cosine a, and one double angle formula for tangent of 2a is 2 times tangent of a divided by 1 minus tangent squared a. Similar to our sum and difference identities, we can use the double angle identities to evaluate trig functions for angles that are maybe not on the unit circle, but half of it is. So we're going to see how that works in these examples here. So given cosine theta is 3/5, sine of theta is less than 0, so sine of theta is negative. Find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. If cosine theta is positive, that means we're in Q1 or Q4. If sine is negative, that means we are in Q3 or Q4. So this tells me that theta is in Q4. And we can start setting up a triangle to show theta. Here's theta. Cosine of theta was 3/5, so the adjacent side is 3. The hypotenuse is 5. That 3 is going to be positive because, again, cosine is positive, and x is positive in the fourth quadrant. Find sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. So let's start with just sine of 2 theta, setting up our formula. Sine of 2 theta is going to be 2 sine theta times cosine of theta. Well, we have cosine of theta that was given in the problem, but sine of theta, we're going to need to complete this triangle. So to complete this triangle, using the Pythagorean theorem, 5 squared equals 3 squared plus our y value squared. So 25 equals 9 plus y squared. Subtracting 9 from both sides, y squared is 16. And when we take the square root, we want to be mindful of the sign because we're in the fourth quadrant. Y is going to be negative, so this is a -4. So sine of 2 theta is going to be evaluated by 2 times -4/5 times 3/5. Multiplying across, we're going to multiply 2 times -4 times 3. This is -24. And 5 times 5 is 25. So sine of 2 theta is -24/25. To evaluate cosine of 2 theta, I'm going to go back to my formulas above because we do have 3 options for evaluating cosine of 2 theta. I'm going to use that second formula, the second version, 2 cosine squared theta minus 1. And the reason I'm going to do that is because it doesn't require me using any other values that I had to calculate by hand. In that sine of 2 theta, we had to use that value for sine theta that we calculated. So if there was an error made there, then that first function value is going to be incorrect. But for cosine 2 theta, I don't necessarily need to have an error based on that miscalculation that could happen here. Now, obviously, we hopefully are making, finding these values correctly. And so using either of those other 2 versions for cosine 2 theta would be just fine. But just as a rule of thumb, we try to use the values that are given as much as possible. So I'm going to use 2 cosine squared theta minus 1. Cosine theta was 3/5, and we're going to square that value. Minus 1. 3/5 squared, we're going to distribute that square to the quotient, that ratio. So this is 9/25 plus 1. 2 times 9 over 25 is 18 over 25 plus 1. And if we were to get I'm sorry, this should be a minus 1. I've made that mistake in those last two steps. It should be minus 1. 18 over 25 minus 1. If you were to find a common denominator of 25, we get negative 7 over 25. And you could also do this in Desmos. And then tangent of 2 theta, we really have two options for tangent of 2 theta. We could use the formula above. So 2 tangent theta over 1 minus tangent squared theta. And looking at our triangle, we can see that tangent of theta is negative 4/3. So 2 times negative 4 over 3 divided by 1 minus negative 4 over 3 squared. Start simplifying this. 2 times negative 4 over 3 is negative 8 over 3. Divided by 1 minus, and then negative 4 over 3 squared is going to be 16 over 9. Now, in a previous video, I did show this technique for simplifying a complex fraction by considering the common denominator of all terms. So the denominator in this numerator is 3, 1, and 9, so that LCD is going to be 9. So if I multiply the numerator by 9 and the denominator by 9, it should clear out that complex fraction. Negative 8 over 3 times 9. The 9 and the 3 cancel out, so this is negative 24. And then I need to remember to distribute that 9. So I've got 9 times 1 is 9. And then if I think about 9 times 16 over 9, those 9s cancel out. So this just becomes minus 16 or negative 24 over negative 7. And because we have a negative divided by a negative, this simplifies to positive 24 over 7. Now, the other option for evaluating tangent of 2 theta is using that quotient identity for tangent, which is sine of theta divided by cosine of theta. Because it's tangent of 2 theta, we can still use that quotient identity, just making sure that we use the correct argument. This is going to be sine of 2 theta divided by cosine of 2 theta. And this works really nicely in this problem because we did already calculate sine of 2 theta and cosine of 2 theta. If you were just asked to evaluate tangent of 2 theta, you wouldn't necessarily go through using this because it requires 2 formulas versus 1. It just depends on kind of what you've already done at that point. So sine of 2 theta was negative 24 over 25 divided by cosine of 2 theta was negative 7 over 25. Those denominators of 25 will simplify to 1, leaving us with negative 24 over negative 7 or 24 over 7. Find the values of sine theta, cosine theta, and tangent theta, given that cosine of 2 theta is 4/5 and theta is between 90 and 180 degrees. So if theta is between 90 and 180 degrees, that tells me that theta is in quadrant 2. So I'm going to set up my picture. Now, before I can start labeling my picture, I do want to figure out some of these values, in particular, cosine of theta. If I know that cosine 2 theta is 4/5, I can go back and use one of these formulas to either find cosine of theta here or sine of theta. So I'm going to look for cosine of theta. So we know cosine of 2 theta is 4/5 is equal to 2 cosine squared theta minus 1. We add 1 to both sides. We get 9/5 equals 2 cosine squared theta. And then multiplying both sides by 1/2. I'm saying it multiplying by 1/2. It's the same as dividing by 2, but when we've got a fraction on the one side, thinking about it as multiplication of a fraction is a little bit easier than division. So this is 9/10 equals cosine squared theta. And then we're going to take the square root of both sides. Cosine theta is equal to, and when we draw that plus or the square root, we want to think about whether it's going to be positive or negative. This is going to be 3 over the square root of 10. And when we think about the sign, because we know theta is in quadrant 2, cosine is going to be negative. So now we have that ratio for cosine, which tells me that the adjacent side is going to be -3 and the hypotenuse is the square root of 10. Notice I'm not trying to rationalize at this point, simply because I'm just trying to label my picture. But when I go to state the value for cosine theta, I will rationalize at that point. So now we can start finding sine of theta. Sine of theta, we're going to have to do some more work on that triangle. So using the Pythagorean theorem, the square root of 10 squared equals -3 squared plus y squared. 10 is equal to 9 plus y squared. Y squared is equal to 1. And because we're in the second quadrant, y is positive, so this is going to be +1. So sine of theta, opposite over hypotenuse, is 1 over the square root of 10. We're going to multiply by the square root of 10 over the square root of 10 to rationalize. Square root of 10 over 10. Cosine theta, we just saw that as -3 over the square root of 10, but now we're going to rationalize that. And tangent theta, we're not going to use the quotient identity sine over cosine because that involves radicals. We're going to use opposite over adjacent. So 1 over -3 or -1/3. Verify that sine x plus cosine x squared is equal to sine of 2x plus 1. We're going to modify the left-hand side by foiling. So I'm going to write this out twice just because I think it helps us to see how we're going to FOIL. Make sure we keep both sides of that identity written in each step. Sine x times sine x is sine squared x plus sine x cosine x plus another sine x cosine x plus cosine squared x equals sine of 2x plus 1. Now I see a sine x plus cosine squared x. That's our Pythagorean identity, so that's going to be 1 plus, and then we have a sine x cosine x and another term of that, so we have 2 sine x cosine x equals sine of 2x plus 1. And then this 2 sine x cosine x, if we look back at those formulas, that is sine of 2x. Tangent 8 theta minus tangent 8 theta tangent squared of 4 theta is equal to 2 tangent 4 theta. So looking at this, the left-hand side again looks a little bit more complicated. So let's start working with that. And one of the first things I notice here is that there is a factor of tangent 8 theta in both of those terms. So I'm going to factor that out. So tangent of 8 theta times the quantity 1 minus tangent squared 4 theta is equal to 2 tangent 4 theta. Looking at tangent 8 theta, 8 theta is just 2 times 4 theta. So we kind of think about this as our 2 times a. So if I rewrite tangent of 2 times 4 theta or tangent of 8 theta using our double angle formula for tangent, that becomes 2 tangent of a, or in this case 4 theta, divided by 1 minus tangent squared of a, or 4 theta. This is being multiplied by 1 minus tangent squared 4 theta equals 2 tangent 4 theta. And both these expressions of 1 minus tangent squared 4 theta in the numerator and the denominator simplify to 1. So we're just left with 2 tangent 4 theta equals 2 tangent 4 theta, and we have verified that identity. Simplify the expression. So in this example, we do not want to grab a calculator. We want to give an exact value. 1 minus 2 sine squared of 22.5 degrees. So we're going to let A be this 22.5 degrees, which means that 2A is 2 times 22.5, or 45 degrees. Using these substitutions of A, this can be rewritten as 1 minus 2 sine squared A, which is one of the formulas, or is part of the formulas for our double angle formula for cosine. So this is cosine of 2A. We know what 2A is. 2A is 45, so this is cosine of 45 degrees. And cosine of 45 degrees we know is the square root of 2 over 2. 2 times tangent of 15 degrees minus, divided by 1 minus tangent squared 15 degrees. Again, we're going to say that A is 15 degrees, which means 2A has got to be 30 degrees. And this expression is representing 2 times tangent A over 1 minus tangent squared A. Which is our formula for tangent of 2A. That's our double angle formula for tangent. 2A is 30 degrees, so what we're really evaluating is tangent of 30 degrees. 30 degrees, I'm using that technique that I illustrated in my video. That creates sort of that shorter, or that flatter triangle in the first quadrant, which means that my x is longer than my y. So my x coordinate is square root of 3 over 2. My y coordinate is 1/2. Sine is y over x. So this is going to be 1/2 divided by the square root of 3 over 2, which simplifies to 1 over the square root of 3. And to rationalize, we multiply by the square root of 3 over the square root of 3, or the square root of 3 over 3.